Hello and welcome back to another episode of Math with Sohn. Today we're going to continue AP Physics. We're talking about elastic potential energy as well as work and kinetic energy, and we're going to be talking about it with springs involving Hooke's law. Now, Hooke's law indicates that the force required to compress a spring is correlated to how far you have to stretch it or compress it times this K, and this K is a constant, okay? That constant is dictated by how stiff or how thick the spring is. And if the spring is really thick, it would be really hard to compress at a very big distance. Or if it's really flimsy, then it would be a low amount of effort and a small amount of force that would be required to be able to compress it. All right, and that energy is conserved and it is stored within the spring. It wants to boing out with that. Now, connecting it to energy, the work required to stretch a spring. Remember, the work required to stretch a spring would be the change in kinetic energy, which ends up being your potential energy. Okay? It is, for springs, the U elasticity, the potential elastic amount of the spring. Now we're gonna derive the formula using this little graph here. So if you were to graph F is equal to negative kx, we're going to ignore the negative sign because that really just involves that the force required is opposite of the displacement. If you think of it as F is equal to kx, that would mean your k is your slope and your x is your just y equals mx. Okay, so it'd have a y-intercept of 0 and it would be going up 1 over 1, or whatever the k would be actually your slope. If it's a bigger k, the amount of force would be even higher. It would go up quicker. If it's a smaller k, it would go up slower. All right? With that in mind, knowing that force is equal to kx, this F is essentially kx. And if we wanted to find the work, just like our last video, we would want to find the area underneath the curve. So that would mean that our work would equal F times d, which would be typically F times x. But our work in this case could also be called kx because kx is what the force is equal to. Kx times x. And it is a triangle, so we would need to do 1/2. Okay, and if we multiply the kx times x and the 1/2 and everything together, you would find out that the work required to stretch a spring would be 1/2 k, the same k as before, x squared. Okay? So with that in mind, we would then know our U elastic is 1/2 k x squared. The potential energy, the work, and the kinetic energy, as long as these are conserved of energy and are not losing any, which is unrealistic, but for AP Physics 1, they tend to say, oh, there's no friction in a spring, they will all be equal. Okay? So, another note is that typically springs are used, but you could also talk about a rubber band or a tennis racket or a bow and arrow or anything else that would kind of be springy and make a boing sound. All right, we got one example for springs. A spring is stretched 10 meters by a force of 75 newtons. We're going to have two parts to this question, but they're kind of separate. The only thing that's going to be consistent is the spring. All right, so a spring is stretched 10 meters, force 75 newtons. What is the spring constant of the spring? A little repetitive there. So what is the spring constant? Well, the spring constant we would know would be F is equal to kx. The negative is just for displacement. That'll be in a different video where we explain why it's negative and get really detailed for that. But for right now, because force can be thought of as positive, and if we make it negative, it makes it messy. So force, what is the spring constant? We know the force is 75 newtons. That would equal k. We don't know what k is. But we do know it was stretched by 10 meters. Well, that's a simple one. You can divide by 10. And when you divide by 10, you find out the force is equal to 77.5 Newton meters. Better known as 7.5 Newton meters. So, part B. That's the one that's a little bit harder. The spring is placed vertically and a 3 kilogram watermelon is hung from the same spring. We are no longer stretching it 10 meters with this force. Okay, this is a separate scenario. It's just the same spring. So this spring is attached to a ceiling over here. Spring, and then you got a watermelon kind of just, right there. There's your watermelon. You got gravity pulling down on the spring, and it would have to be matched by the force of the spring. So if we have the force of the spring and gravity, they're in equilibrium. So the force that the spring is storing up will have to equal the force of gravity that is pulling down, okay? So we want to calculate that elastic potential energy stored in the watermelon, elastic potential energy stored in the spring, not the potential energy of the watermelon. I'm assuming this watermelon's like, in dire straits of like falling and crashing on the ground, but we don't care about the watermelon. We care about what is being stored in that spring. Okay, so with that in mind, mg will have to be equal to force of the spring, which is kx. So mg would have to equal kx. So the force of gravity times how much this thing weighs times gravity would have to equal the force of the spring, which is kx. We could solve for distance because we want to know, we have everything else, so we might as well solve for distance. So that would mean that we would divide by k, mg divided by k. And if we know our distance, that would be very helpful. So let's plug in our mass. Our mass is 3 kilograms. Gravity would be 10 meters per second squared. You could also say 9.8. And we need to divide by our spring constant. Remember, the only thing consistent with this problem is that the spring constant is the same because we use the same spring. And I imagine this spring is hurting. Then again, it could stretch 10 meters before, so maybe it's a really big spring. All right, if we do the math here, then we would end up with 4 meters. That's the distance that it moved. That's important because if we know the distance that this spring has stretched down, if it has gone 4 meters down, then we could figure out the potential energy stored on the spring. What was our formula for potential energy of a spring? 1/2 kx squared. Okay. Well, that means that 1/2 kx squared, we know our spring constant. We now know our x. We can plug in all our stuff. So that would be the force of our spring is equal to 1/2 k, which was 7.5 Newton meters, and our x, which is 4 meters squared. If we do all the math here, you would end up with 135 joules. Okay, so that's going to do it for this one. Continue looking on into the future ones. We're about to get into conservation of energy. All of this is really starting to tie in with each other. So depending on which playlist you're in will depend on what's going to happen. So if you're in the harmonics playlist, we're about to get into pendulums and so on and so forth. If you are in the energy playlist, we're going to get into conservation of energy. So both of these kind of tie in just like all of physics. Don't worry, we're going to get through it together. I will see y'all then. Bye.